Okay, all right. So what we are about to do here is just to finish what we started last time, which talking about heat, and we are just looking at some perspective of, so now it's sort of like what it is or how to calculate those, and then we're gonna make the connections from heat to something else under thermodynamics theory. Okay, sounds like a good plan. Yeah. All right. So before we move on to things that we would like to do today, let's start with this sort of like, I think this is a good problem for you because this kind of problem will show up in the exam. So at least you will have a chance to see that how what is the level of difficulties that you're going to face in the exam. So it's not too bad. All right, you'll see that. Okay, so let's start with this one. So we use this exercise as a review of what we did last time. A poorly designed electric device has two bolts attached to different parts of the device that almost touch each other, okay, inside this device. Okay, so when they touch, a short circuit will develop and damage the device, which is not good. If the initial gap between the ends of the bolts given to be 5 micron at 27 degrees Celsius, at what temperature will the bolts touch? Is that good? I think this is about right. Okay, so this kind of like a good level. It's like an exam question level. It's not that difficult, but I know at least you have to apply something to it. However, when you look at this one, it's still, I would consider this one is very straightforward because I mean the bolt is already attached on both sides. I mean on each side of the wall of the interior part of the device. So the expansion will happen to only the open ends of the bolt. So that means when you warm this thing up, the steel will expand to the right and the brass will expand to the left. And eventually they're going to touch at some temperature. Does that sound good? All right. So that's kind of like, okay.
Okay.
So the concept is kind of like straightforward in the sense that once they touch, it means the expansion from both bolts gonna have to fill up this gap. So this will contribute by the expansion from, let me use a subscript ST, that is the change in the length from the steel, plus there will be the expansion due to the brass. So let me call it this delta L with the subscript B. Sounds good, okay? And then of course, once I have these two added together, eventually it's going to be equal to the length of the gap. And that is it. Simple enough. All right.
Okay.
Okay, so what we need to do is just taking care of the change in the length of the steel plus the change in the length of the brass. All right, how much is this? All right, from last time, we can calculate from taking the alpha, the coefficient of thermal expansion of the steel. So let me put the subscript ST in down here, times the initial length of the steel bolts in here, which is 0.01 meter. So let me put 0.01 meter right here, times the temperature change, because we don't know what is going to be the final temperature. Let's call that temperature X. So if they're going to touch at X degrees Celsius, so the temperature change will be X minus 27 degrees Celsius. Sounds good? Already, that's not bad. And then you add this with, all right, so let me color code it here a little bit. The increase in length for the brass. Doing the same thing, you have the alpha, the expansion coefficient of the brass, times the initial length of the brass, which is 0.03 meter. And of course, they're going through the same temperature change. So that means it's going to change by X minus 27 as well. Cool. All right, once you're done with that, you equate this with 5 micron. Here we go. So let's do a quick check on the unit conversion, shall we? All right, every time you look at the 5 micron, first of all, you have to know what the micron is sort of like stand for. This one is 10 to the negative 6. That's for the micron. So that means if you want to convert that micron into meter, which is our SI system that we're going to stick with, so you just times 10 to the negative 6 meter. All right, so everything is good. The units are all in SI system and everything. So all you need to do is solve for X and you're done. Okay, and of course you can look up the alpha from the for the steel and the alpha for the brass from the tables or from the web and on and on. All right, you should be able to get the X as your final answer. Sounds good?
Okay.
Done. All right. So I think this is startup showcase what kind of questions that will show up in the exam. Is not going to be like too complicated, but I hope these two exercises give you like very good representations of what's going to happen. All right. But anyway, you can find more in the exercises that is going to show up in the course. So wait for those. All right. Any questions so far? Sounds good. Already. All right. For the number, you just sort of punch your calculator later. Okay. I don't want to do it. All right. Sometimes, like when doing the sort of like numerical calculations on screen or live, sort of like tend to make mistakes. Right. We will see all the time. All right, guys. So, what we are going to do next is we're going to dive a little bit deeper into the matter. And we're going to eventually pick a good one, the one that actually very useful in understanding thermodynamics. All right, it can showcase so many properties in thermodynamics. However, everyone knows that matters can have three states. Okay, one is in solid, either in liquid or as in gas. All right, even though you might have said like there are like fourth state, fifth state of matter, but anyway, just for just a common states of matter, you are dealing with these three states. All right, and everyone knows solids are the one that has molecules pretty much jam packed and very sort of like stuck together in a very solid manner. The gases, on the other hand, just go all over the place. All those atoms and molecules in gases are freely moved. All right, they interact very small, very like minimally, and we assume that they can fill up all the volume in the container all the time. And then the liquids come in between. Somehow it has some interaction, right? However, it still have a ability to change the shape of the liquid itself, depends on the shape of the container. So these are the whole thing depending on like a fine detail of interactions between molecules inside those matters. Okay. All right. However, what we really care about so much in this topic is we are going to use gas phase as our sort of like think of it like a system that we are going to study. Okay. The why is that? First of all, it's well, it's not very complicated. You might say solid is also not very complicated, but the bad thing about the solid is it doesn't showcase the expandability because you're going to see later that we need some action going on. But the solid is like, it doesn't show up much. I mean, if it expands, like you saw from last topic, it's very minimal. Right? The expansion is super small. So you won't be able to see much of the expansion from the solid phase matter. Okay, sounds good. All right. Liquid. Well, I mean, it doesn't have like a grand equation to describe the state of the liquid. It's kind of like, okay, well, this depends on the type of liquids. You learned fluid dynamics before, but you haven't learned about like, hey, how can you describe the property of liquid properly? But when you look at the gas, you remember one thing about gas. You have heard of the word ideal gas, have you? Yeah, I think so. All right, that's like, oh, that's an ideal gas. And every time we talk about ideal gas, one thing that comes into your mind is like PV equal to nRT. Does that sound familiar to you? Okay, that's kind of cool. Okay, that we have a relationship that's sort of like link between the macroscopic parameters that you can measure. You can measure pressure. All right, that's easy. Volume. All right, now we can see some action, right? It can expand, it can contract. So you can sort of like, okay, take a look at what is going on under thermodynamics microscope. And temperature, that's the main goal of us. So this is great. So this is the reason why we're going to stick with the gas mostly. All right, even though thermodynamics works in all types of matters, but gas is a really good sort of like system that we can use it as like a, like, okay, all right, it's our system for studying. All right. So, and then we have a word ideal over here. So for you to be able to utilize this expression, you need the ideal environment. You want an ideal environment. The environment that we're talking about is supposed to have a low pressure or, combined with the high temperature. The reason for that because we want all those molecules here, there, this, that, to stay apart. You don't want them to stay so close to each other so much to minimize the intermolecular forces. All right. So we would like them to interact minimally. And for the ideal case, we're going to assume that there are no interactions whatsoever. Is that cool? So that's the kind of thing that physicists have to start from something simple, manageable, and then we're going to build the complexity on top of those. All right. So we're going to start from something super simple, no interactions. All the atoms or molecules stay far apart. And I mean, you still allow them to collide with each other. That's no big deal. The collision happens. That's fine. All right. However, we assume that that collision will be perfectly elastic. So that means there will be no loss of energy or anything during the collisions. All right. And that's it. So that's the ideal gas that we want. All right. And once you have this ideal gas, all right, this equation is valid, works. This one works. Okay. All right. So to be able to use this one, you see that now you have some variables. You can vary the P, the V, and the T. We'll go into detail later for each of them. All right. Plus, you also have something next to it. There is some constants that has to be thrown in this equation there. So these combinations of the stuff can combine together and describe the state of the gas. So I hope by talking about this for 5 minutes, you can see why we stick with the gas, because we don't have this kind of equation for liquid. I don't think we have that. We don't have this kind of question for the solid. So gas is the easiest system to study. Okay, cool. So I hope I give you enough motivation to move on with this. All right, here we go. So what are the states variables that we have to deal with? Pressure, I think you guys learned this one already in fluid dynamics. It's just a common concept saying that it's a force per unit area. All right, and then we talk about this one is a force per unit area that is sort of perpendicular to the direction of force, or you can think of like the force fall perpendicular onto a surface. But the ratio between force per unit area, that is the pressure. But the good thing about the pressure is you moving yourself away from this force right here. It's a microscopic stuff that we don't want to deal with anymore. Yeah, we discussed this last time. All right, next, temperature. All right, you can measure that using thermometer or whatever that you want to make measurement with. Volume, all right, that is another macroscopic quantities that you can measure all the time, the width, the length, the height, or whatever you want. Now, you also want to know the number of molecules of the gas. We use capital N for that. Okay, this one is a counting numbers. So it's just 1, 2, 3, 4, 5. And we discussed last time that's the number that we are dealing with is going to be in the order of 10 to the 23rd, somewhere around there. It's like millions, and some more. All right. So that's the one that we're going to deal with. However, because we know that you have talked about these numbers before, let me use a subscript A for this. Is the Avogadro number. Is a special number, and it's put that number down here. Is about 6.023 or 22 in this case times 10 to the 23rd. This is numbers that's saying that if you are dealing with an ideal gas, it doesn't have to be ideal gas actually. This is a unit. Let's say if you grab this many molecules, 6.022 times 10 to the 23rd, you will call this 1 mole. So that is another unit that I think you have used this in maybe chemistry, right? 1 mole, a mole of gas will be equivalent to this N sub A numbers of molecules. Okay, so that mole that we defined, it means you just take this Avogadro number that's constant over here and divide it with the N. So you take the N, the number of molecules, and you divide it with that Avogadro number, you will get the small n. That is the number of mole. So it's right here. There, number of mole. Sounds good? Are you guys familiar with this? All right. For those of you that not familiar with this, don't worry. It's actually, this is simple as you buying a dozen of donuts, right? A dozen is like 12, like a dozen of donuts. All right. So every time you take one dozen of donuts, that is 12 pieces. That's what it is. So it's a 12-piece donuts. Same thing over here. If you have 6.02 times 10 to the 23rd molecules of the molecules, right? You call this 1 mole. All right. So that is just a conversion factor. That's all. But number is just not 12, but it's just big, huge number over here. All right. Sounds good? Okay.
Okay.
All right. Then, so we're going to have to deal with these two numbers, right? It depends. It depends on the information that you have, or it depends on what you like. So you either deal with the number of mole, or you are dealing with the total number of the molecules or atoms in your system. Okay, so there's capital N, that's the counting numbers, and small n, that is the number of moles. Okay, now there is another one that if you really want to, is the mass, because we deal with mass a lot in Newtonian physics. But it turns out, because you can always refer to mass later every time that you know the number of molecules or number of mole. So in general, every time you talk about the mass, it's kind of like, well, it's just another kind of conversion that you have to convert to. So you will see that for the rest of the lectures, or the rest of this module over here, we barely use molar mass or total mass. All right. The molar mass is just the mass of 1 mole of gas. So that's it. All right. So it depends on what you want to talk about. But usually we don't talk about the mass of the gas anymore. It just maybe because you don't want to weigh it, I guess. Gas is just running around. Well, yeah, you just pretty much want to count them. You don't want to, weigh them, I guess. มันคงชั่งน้ำหนักไม่ได้เนอะ I guess. All right. Anyway. Yeah. Okay. All right. So stick with the n. All right. Stick with the n. All right. So with these sets of variables, you are able to figure out the state of the gas using the equation of state right here. All right. So that's it. So welcome, you guys, to the first. Oh, that is the second equation already, right? We did the first equation, but this is the equation that I can classify this one as a law, even though it's not like a law per se, but it's sort of like it's a specific relationship that is always true for the ideal gas. All right, so this one is way, well, it's not better or worse, but it's way restricted than just the equation that we use for the expansion from the last topic. Okay, so over here, the equation that we are using is P, pressure, times the volume, is always going to be equal to the product between the number of mole of gas, the small n, times the temperature. And then you squeeze in this constant over here that we're going to have the name for. It's called gas constant, or universal gas constant. And it has a specific value of this one, 8.31 joule per mole Kelvin. All right. And if you want to pair this left side of the equation with the capital N, all you need to do is you just convert that small n here, because the number of mole is just the total number of molecules divided by Avogadro number. All right. And that will lead you to this right here. So you will have, let me highlight that one. You have R, that has the n sub a, the Avogadro number in the bottom. So this ratio over here will give you another constant, right? Because R is constant, n sub a, the Avogadro number, is constant. So the ratio of those two constants will give you another constant. And that constant has a name. Let me use different color here. It's called Boltzmann constant right here. And it has a specific value right there as well. Okay, guys, sounds reasonable? So if I want to write it down at the end, what I'm having right now is you can use PV equal to nRT. If you have a small n, which is the number of mole, you pair this one with the R. Or if you have the number of molecules, the counting number, you pair this one with the K. But the structure of the equation stays the same. PV is proportional to the temperature directly. all right, and multiply by the number of molecules. Depends on the units that you're going to pick. Is a mole or it's just a total number. Okay, cool. And the key thing that you really need to stick with every time that you apply this equation is the T right here must be in an absolute scale. Because this is a pure equation, this is the sort of like a strict relationship of the ideal gas. This one has to be in Kelvin units. All right, you cannot substitute degrees Celsius, everything in there. This has to be a Kelvin scale, the absolute scale. Okay. However, this is the good thing about this one. The delta T in Kelvin is going to be the same thing as a delta T in Celsius, right? We learned from last time that the resolution, the steps in each scale are exactly the same. 1 degree change in Kelvin is the same as a 1 degree change in Celsius. So if you are dealing with the change, it's okay. You don't need to convert the units. Okay. However, if you want just the value of the temperature in an equation, usually most of the time you will need that temperature in absolute scale or in Kelvin. Okay, sounds good?
Okay.
All right, just to be careful. All right. If just a plain equation, stick with the absolute scale. But if you are dealing with just the change, then you can use either scales. Doesn't matter. Same thing. All right. And the good thing about this one is for those of you that has already taken chemistry, you probably remember this kind of thing. If I sort of move things around a little bit, if I move temperature on the left-hand side and then I just leave whatever left on the right side there, you can see that as long as you have a gas system that doesn't change the numbers of gas, I mean, there's no gas leak, there's no addition of gas into your system or whatever. So that means the right side of this equation is a constant. Okay, so that means if you have a system with a fixed amount of gas, you can manipulate this gas no matter what you want. You can expand it, you can sort of like, compress it down, increase the temperature, do whatever you want. This ratio right here, PV over T, must stay fixed. Does that make sense? Okay.
Okay.
All right. So with that gives you a very, very easy comparisons between two states of gases. Every time that you have one gas, this gas, you're not changing everything, I mean, anything of this gas at all. And then you just manipulate those variables. No matter what you do, this PV over T stays the same, no change. So this is the reason why you can write it as like P1 V1 over T1. That is just for first scenario or first state of the gas. And then you change everything, P2 V2 over T2 must stay exactly the same. Okay, so this is going to be very useful later. All right, but for now, that is the introduction or maybe the revision of the gas equation or the equation of states. Okay, no? Not too bad. All right. วันนี้อาจารย์พูดรู้เรื่องไหม
Okay.
พอได้นะ All right. Okay. All right. So with that, let's sort of, practice a little bit, how things go. Just, ease you guys into the material. All right. It's going to get tougher the week after this, but all right. This one is just keep going. An ideal gas occupies a volume of 100 cubic centimeter at 20 degrees Celsius. And given the pressure of, what's that? 10 to the 6. So let me change that to here. All right, the exponential number over there. Okay, so determine the number of moles of the gas in the container. All right, they just want to figure out the number of mole. So that means here you want to figure out the small n. That's what you want. There you go. Also find the total numbers of the molecule. So this one you want the capital N. All right, so let's do an easy exercise right here. This is going to be just plug and play type of question. There you go. So if you want a small n, the number of mole, you use PV equal to nRT. All right, the sort of like annoying part of this problem is just the units, just all over the place. The pressure first. The pressure is 10 to the 6. Good. It's in Pascal, which that's a SI system for the pressure. So that is perfect. Pressure is good. Now the volume, it's in cubic centimeter. You don't like that because you want cubic meter as long as you would like to use the SI system. I would like to have a quick check, guys. How can you convert this 100 cubic centimeter to cubic meter? I don't know how you guys sort of like do this in general, but the way that I'm doing this is this. Because I know, okay, let me write it down here. Centimeter cube, right? This is a cubic centimeter. Every time that I see this kind of prefix in the unit, we know what the C means. It's 10 to the negative 2. Right? So in my head, I am looking at two numbers that is multiplying each other. You guys with me? So this is just like two numbers multiplying. That's it. That is just meter multiplying with 10 to the negative 2. And it's cubed. So that means what I'm doing over here is I can just manipulate this one just like I'm manipulating numbers. So what I'm doing over here is going to be 10 to the negative 6, and I have meter cubed left. You guys with me? All right, so that's it. So I can convert from cubic centimeter to cubic meter very easily by just pull that 10 to the negative 6 out. But I'm not pulling out anything. It's a product. So, all right, let me write it out here. It's 100 cubic centimeter. It's going to be 10 to the negative 6 right there. Cubic meter. Sounds good? All right.
Okay.
All right. And this kind of techniques actually works all the way through whenever you, I don't know, you like this or not, but if you like this one, just take this. For example, if I have 5 cubic meter, and if I want to convert this one to micrometer, cubic micrometer, which is kind of weird, right? But anyway, I can do that. I can turn this into a cubic micrometer by doing this. I multiply by the 10 to the negative 6, make it a micron. And then I divide it out by a micron. See, I'm not doing anything. You guys with me? Okay. And then I'm just going to keep that micrometer here, just leave it there. So what I'm having out here is just another extra micron factor that get cubed and is dividing 5. So what I'm having over here is going to be 5 over, let me write it like this, micron cube. Sound like that. I hope it's okay. And then I have the cubic micron. That's what I want. That's my final unit that I want. And then at the end, it's going to be 5 times. So this one is 10 to the negative 18. All right. And then I can just flip up, and then it's going to be 10 to negative plus 10 to the 18th cubic micron. And that is done.
Okay.
All right. So I don't know you like this method or not, but if this one sort of help you eliminate the confusion every time you want to convert the unit from small to big, of big to small, and then you have to memorize like, okay, going from small to big, you have to divide, going big to small, you have to multiply, and then just sort of, going all over the place, then just treat the prefixes to be just a number that is multiplying other numbers on your expression. All right. And I think it will make less mistakes. That's my take on this one. Okay, come back to our business here. I don't know, I'm talking way too much or not. Here we go. So PV equal to N, that's what you want to figure out. R, that's already a constant, so we can plug it in anytime you like, times the temperature. Here we go. So the temperature that you want to squeeze into this equation must be in an absolute scale. And that's where you want to convert this. All right, let me just take 273. That just, right, you don't need to be super precise here. And then you just add 20 to it. That's how you convert it into Kelvin scale. And that's it, guys, done. So from here, you can figure out what should be N. All right. And then, of course, if you want to calculate the capital N, the total numbers, all you need to do is just pair this thing up with another pair, the capital N with the Boltzmann constants. But then you still have to add the same numbers over here, 273 plus 20. So from here, you will be able to calculate the capital N. Done. Or, of course, you can always convert from the number of mole back to the capital N, the total numbers, by just saying that it's going to be N times the Avogadro number. That will work too. All right, same thing. All right, sounds good.
Okay.
All right, nothing surprising at this point. So far, so good. All right, next. Try this one, guys. Okay. Just kidding. All right, guys, try this one. So you have a pure helium gas and is admitted into a tank containing a moving piston. So it means there is something that can change the size and everything now. Now the initial volume, pressure, and temperature of the gases, they're all given here. If the volume decreased to a new value, so it means somehow it gets squeezed, and the pressure is increased to a new value, what will be the final temperature of this gas? See, so this is a type of question that actually you would like to compare between two states, right, of a gas. So all you need to do is just use that relationship that we already derived there. P1 V1 over T1 equal to P2 V2 over T2. Yeah. The reason I make this kind of sounds is kind of like boring a little bit. I don't know. This is like back in the chemistry day. All right. Anyway, so what you have to do is just, all right, make sure that you use the same unit on both sides. You will be okay. All right. On the left, let's start from the pressure. The first pressure over here is given to be 200 kilopascal. 200 kilopascal. All right. Because it's a comparison between two sides, so you don't need to convert the unit in this case, because as long as the right size of the equation will be in the kilopascal units, you okay. All right, so let me equate that. Keep it there. All right, we'll go through that later. Now the volume is right here. All right, it's 15 times 10 to the negative 3. So 15 times 10 to the negative 3. Unit is good already, cubic meter. That's nice. Okay, divided by the temperature. The temperature is given right here is 300 Kelvin. Wow, nice. So it's already Kelvin. So you don't need to convert anything. All right, cool. That's the first state of this gas. Now things change to a new value, but now the new value is given to be 350 kilopascal. Perfect. Same unit. So I'm just going to take that. Don't need to convert anything. Now, the temperature that is changed, that's what you want to figure out. Just leave it there as your unknown. And then you subtract, divide this by oh, sorry, it's a wrong place. my bad. sorry. Right. You guys are wondering, well, wait, then temperature is down there, not up there. All right, volume first. The volume. Here we go. The new volume is 10 times 10 to the negative 3. Let me put it like 10 to the negative 2 right there. Oh, actually, well, just leave it there, just for clarity. There you go. All right. There. Okay, and then now you divide this by the temperature, and then you can figure out the new temperature there. Done. Okay.
Okay.
Not bad. This is good. So that's how you can utilize the equation of states to deal with the gas. All right. Any questions so far? It's kind of easy enough for you. All right. Next. Now let's come back to our business of heat. So just leave that park there for a while. All right. We'll have a chance to come back and talk about the gas. However, because this is the topic about the temperature and heat, so let's come back to the heat business a little bit. And then eventually next week, we're going to combine them all. All right. So I'm asking you guys, because sort of like, I think everyone is so familiar with heat. And we talk about heat all the time. I mean, then heat, everything is heat. And like every time when there's like, it's getting hot, and then there must be some heat in that situation all the time. What do you think heat means? So this is kind of like I think you hate this kind of question, right? Because it's so broad. It's like, what is heat? And then, Ajahn just asking, throw this one out, and nobody will. I don't know how to answer this one. It's so crazy. So what I would like to start this is by asking you, how do you feel about this word? Here we go. What do you think? Mm. Just kidding. All right. How do you feel about the word heat energy? Is that good? Is bad? Or it's all right? Or it's okay? Or it's just like, what is going on? All right. Hot air. All right. Hot air. That's on fire. Okay. There's somebody saying like on fire. All right. So technically, there are two words in here, in at least in physics, that we are dealing with at this point, is heat and energy, right? And we learn energy from Newtonian physics. And this energy eventually will link to, like, force times this displacement, and then you get the change of the energy. You have to calculate the kinetic energy, potential energy, on and on, right? But then what we are dealing with at the moment is this one heat. And now I combine these two together into a heat energy. All right, for those of you that seems to sort of like, okay, if I'm going to translate this one, just talk about it from the perspective of just language, it looks fine, especially in Thai. It looks really good because this one is พลังงานความร้อน All right, I'm not sure. Maybe some of you cannot read Thai here, but I mean, in Thai, the heat mean ความร้อน Okay, that's the word. And energy, that is just, of course, energy is พลังงาน. So when you combine these two, it sounds okay. พลังงานความร้อน. That's good. But it turns out this is illegal. When it's illegal means that you cannot use this one in physics, or actually anywhere in this universe. Actually, you cannot use that because there is some conflict in terms of the meaning of these two words. Okay, and I'm going to show you that. So the correct word for this is supposed to be thermal energy. All right, this is the one that we use all along because we have this thermal stuff until we get thermodynamics, right? We use the thermal, that's the adjective that we're going to use here. This one is good, but the bad thing about Thai language is you can still translate thermal into ความร้อน anyway. So that means seems like thermal energy and heat energy seems to translate it into a single same complex, which is พลังงานความร้อน. But anyway, the reason that we cannot use heat energy because, here we go, guys. Heat is actually its energy in itself. It's already energy in itself. But not only that, it has to have a transfer mechanism. I mean, there's a dynamic to it already. So that means you cannot use heat to do something just only in, like, you have like a single party in your system and talk about heat. That doesn't work. Heat has to transfer from one place to another place, from one object to the other object, from the object out to the environment. There must be some transfer. There must be some movement going on with the heat all the time. All right. So that's why when you have the word heat energy, it's like there is two energy in this word right here. It's like heat is the energy transfer energy. That doesn't make sense. You don't have any energy in the energy transfer. It's the energy itself that gets transferred. Does that make sense? All right. So this heat is going to be classified into the same class as work. Okay, you guys, I'm getting connections right here. So the W is force times displacement, right? Remember this one. But what was the work that you were talking about? What was it? You were saying, oh, Ajahn, every time you do force times displacement, you transfer energy. Like I'm pushing a table. I'm transfer energy from me to the table. So the table starts to move. From the beginning, the table is zero kinetic energy. But once I push it, I transfer the energy of mine. I might have already had breakfast and everything. I use all those, energy in my body, transfer it to that table. So the table will have kinetic energy to move. So actually work is also energy transfer. And now you can see that now heat is pretty much the same thing. It's also energy transfer. So from now on, heat and work are the same class of parameters or the stuff that we're about to use. However, the energy transfer from the heat is due to thermal effects, right? The one that we discussed last time, when you push a table, you never ask me what is my body temperature, what is the temperature of the table, because you haven't talked about the aspect of the thermal energy transfer. Does that make sense? All right, but now we're going to include that into our consideration. That will be another kind of energy transfer is due to the mismatch of the temperature between two bodies. Okay. And this one is the thermal effect. What you did back here is purely mechanical effect. And once you combine this heat and work, that is thermodynamics.
Okay.
All right. I hope you try to build up some motivation a little bit, like, okay, this topic is interesting. All right. Okay. All right. So that's why I put it here. Heat is not energy contained inside a body. So heat is totally different from 1/2 mv square. No. mgh, no. 1/2 kx square, no. Right? Those are energy that contain in the body. That is fine. Potential energy, kinetic energy is fine, but heat is energy transfer. That's it. All right, so that's give you a whole idea of what is going on now. All right, so to be able to talk about this energy, talk about the energy flow transfer, it turns out people discuss heat or learn about heat starting from learning water. I mean, they study water and learn how the water is sort of like change in temperature. It's get hot, it's get cold, it get frozen, it's vaporized and everything. So there is an extra unit that was built during the time of the water studying, which is a calorie. Okay. However, nowadays we know they are pretty much the same thing. So we have the conversion between the calorie unit to the joules, the one that we use for the energy in SI system. So 1 calorie is equal to 4.2 joules. Okay, but the good thing about having the units calorie is this: water, all right, it has something that has like simple numbers. So that's why this unit of calorie is still work pretty well with the water from time to time. All right, so we just maybe go back and forth between these two units. All right, but at least now we know the conversion between the two is 4.2. Okay, all right, here we go. So James Joule, who was the one who identified that, hey, when every time that we talk about heat, actually it turns out it's equivalent to the mechanical energy. But you have to sort of like realize that back in like 200 years before, or maybe 250 years before, you don't know much about the energy. You don't know much about like, what does it mean by heat? What does it mean by atoms? What does it mean by molecules? You don't know. Okay. So Newton's working on the Newtonian physics. And then there is another school of people talking about heat. Some ghost running around. And then when it's get to one point, it's get hot. When leave that point, it's get cold, on and on. So Jules, who's the one that's trying to say that, hey, heat and work are pretty much the same thing. And you can convert between these two things all the time. All right. Even though I don't want to go back to this sort of like simple conversion, all the stuff like experiments that try to showcase things. But from this simple diagram, you can see that this is the experiment by Jules. He can drop a mass, or actually two masses, down, and there is a linkage to the paddle inside a tank of water. And it turns out he measured the change in the temperature of the water, and he shows from these experiments that he can convert the gravitational potential energy, the mgh, into the rise in the temperature of the water. All right. So that's why he sort of like can come to a conclusion that heat that we're talking about, it's going to have the same meaning as the energy that we talked in mechanical world, something like that back in the day. Okay, sounds good. All right, but anyway, for us today, it's like, okay, we know that. Okay, but another thing that we, before we sort of move on, this is something is good to know, just like a fun fact. You guys probably have already known this. The calorie in the food packaging, like when you see here 230 calorie, you have to notice that it turns out this is a capital C, it's the big cal unit. So on the food packaging, the nutrition facts, it used the food calorie, which is 1,000 times the calorie that we use right here. Okay, you guys with me now? All right, so that means you can think of it like it's a kilo calorie. And this is the one that I think we are familiar with, this kind of packaging over here. The label on the package looks like this. But I think in Europe, I think they use this, which is pretty nice. All right, they pretty much use the SI system. All right, they use, and they have like, oh, okay, we have the calorie for you. We do the conversion for you guys. So that's kind of like more details, food, like nutrition information label, right? But I mean, for us, I think we mainly stick with the calories here. All right, so big cal, that's what it is, 1,000 calories for the food. All right, here we go. So I think this is a good point to stop. I don't know, it's kind of light, I guess. Maybe I talk too much today, but the thing is, we'll take a quick break right here. When we come back, we'll talk about what does it mean by having the heat flowing in and out from a system, and how can we take care of the change of the temperature of that, okay? And what kind of equation that we can use to describe that kind of thing. Sounds like a plan? All right, then. So take 10 minutes break, and then we'll come back, and then we'll talk about the specific heat, and then we're going to learn how to calculate the change that's going on with the energy transfer due to heat. All right, guys, take 10. Okay, so what we're going to do for the rest of today's lecture is just this. All right, I think this is a straightforward logic a little bit. So now you would like to transfer some energy to an object. All right, think of it. You have an object. Okay, and then you throw in some energy to it. So transfer in. Okay, and I'm gonna call this the Q, which is the heat. All right, you take some energy transferred to this objects right here. So the end result of this one is going to rise in temperature. So you're going to be able to measure some temperature change of these objects, because, well, that's the indicator that the object has more energy to it. Okay, we already understood that if the object is like a simple object that's just like gas that we're about to study, when you give this object an energy, the only way that it's going to use that energy is just to move more kinetic energy. And now we know that more kinetic energy means more temperature, I mean, higher temperature. All right, so that's what it is. So to be able to see this kind of thing, you say, okay, John, that is simple enough. So that means that the heat that you throw in must be proportional to the temperature rises. That's simple. All right, so we can turn this into an equation and say how high is the temperature is going to change depends on this constant right here. So you turn a proportional relationship into an equation, and you throw in some constant that is the meaning of saying that this one will give you an idea. Think about this. If C is small, so if C is just a small number, that means that delta T must be big, because the product must be equal to the amount of heat that you transfer to this object. Does that make sense? On the other hand, if C is big, then the delta T is going to small. It's going to be small. All right, that's no big deal.
Okay.
Because the C is multiplying with the delta T. The product is fixed with the amount of energy that you transfer to this object. So when you try to interpret what this C seems to mean, you can say, okay, when it's big, the temperature doesn't seem to change much. When C is small, the temperature change a lot. So this one has a meaning to it. We call this the capacity, the heat capacity. Does that make sense? The reason I'm asking you, does it make sense as a capacity or not? It means you give the energy to an object. If the object has a way to store the energy, like they have like a big, huge space for you to store energy, it doesn't gonna feel much. So that's why the delta T change is gonna be very small. So think of it like you eating, and if your stomach is big, let's say you need a lot of food for you to feel like, okay, I'm full. All right. But if your stomach is small, only a little bit of food, you feel like, okay, I'm already full. Yeah, the degree of fullness, that is your temperature. So I don't know, does that make sense to you or not? So what I'm saying is for an object that has a big heat capacity, the change in temperature will be small because it has a big storage for the energy. So it doesn't have to show up in terms of the temperature change so much. Okay. All right. So that's what it is. All right. However, the bad thing about this C that we're using as a heat capacity here, it depends on the object itself. Is that right? Because you can pretty much like, oh, John, if I bring in like a bigger piece of this material, like I have like a, or like super big one, the C will get bigger, depends on the size of this object. So everyone seems to agree with that. So instead of having the definition of this as a heat capacity of an object, we're going to do something a little bit simpler. We're going to say, hey, let's look at what type of material that you use to make up that object. For example, is it made from metal? Does it make from some liquid, or is it a gas or whatever? And then you multiply by the mass of that. Does that make sense? So it means you are defining the heat capacity per kilogram of that object. And we're going to name that heat capacity per kilogram to be specific heat. Because by looking at the unit is the capacity per kilogram, to get back to the capital C, the heat capacity of the whole thing, you just multiply back the mass. And here comes the equation that we're going to use is just Q, the heat that you transfer to the object, is going to be equal to M mass C, the specific heat, and delta T, and you're done.
Okay.
Okay. And by doing this, the good thing is all you need to do is you just refer to the specific heat value. For example, is it made from aluminum? You just look it up and then, okay, aluminum has a specific heat of this much. And how big of the aluminum piece that you bring in, you just multiply by the M. You get the specific heat of that piece. Okay. If you bring in water, all right, water, that's going to be the one that we use a lot. Here we go. All right. You say, okay, the specific heat of water is this big. If you bring how many kilogram of that water, you just multiply it, and then you get the specific heat of that water that you bring. Okay, so Q equal to MC delta T is going to be the one that we use for our calculation the most. All right, so with that, let's take a look at a quick example. Just asking you, hey guys, sand and water, when you go to the beach, you think which one has a higher heat capacity? Well, I cannot use that one because heat capacity, you have to specify the amount, right, of that sand or water. So which one has the higher specific heat? What do you think, guys? Just kidding. Sand, okay, sand has a higher specific heat, right? Okay, anybody else, participate a bit? Water and sand. Okay, all right, it's kind of 50-50. Oh, okay, water and sand, water and sand. All right, now just bring in your own experience. When you go to the beach, when you run down to the beach, the sand or the water has a higher temperature that you can feel from your feet. Yeah, what do you think? Yeah, the sand's kind of hot, right? It's kind of sand is hot. You know, when you run into the water, it's going to be a little bit cooler. But see this? Remember this one? Anything that shows up hotter, it means the capacity of it is going to be small. Does that make sense now? Okay. Okay.
Okay.
So the answer to the question of sand or water, which one has a higher specific heat? The answer is water, because the water is stay cool. It's still cool right now during the daytime, even though they both get burned by the sun. So the answer is the water has the higher specific heat than sand. Okay, good. All right. And actually, if you come back and take a look at this table, you can see that actually water is big in specific heat, right? It's sort of like pretty much way bigger than all those metal, right? The metal is kind of like, okay, it's not a lot of specific heat value at all. Okay, so you guys with me so far? So the answer is water, guys, because the temperature change during the day is smaller. That's it's an indicator that the specific heat is higher. Yeah, okay, let me give answer the question. Higher specific heat means higher heat capacity. Okay, yes and no. Because the specific heat is per kilogram. That's all. Does that make sense? So the capital C, that is for the whole object. So it depends on how big of that piece of the object. Specific heat is when you having every material of 1 kilogram and compare. So that's sort of like, that's a number that you can compare the specific heat. But if you just want to compare the whole object, then I don't know. You might bring a tiny piece of a large specific heat metal, and then you want to compare with like a big chunk of stuff, but has a small specific heat. Okay, you have to make the product of M and C to get to the capital C. Okay, does that answer your question? All right, so the specific heat is per kilogram. Per kilogram. Okay, all right, take a look at a quick example here. It's plug and play problems again, just to showcase how to use the equation that we are discussing. The temperature of a silver bar rises by 10 degrees Celsius when it absorbs 1.24 kilojoule of heat. All right, cool. So this is the Q. This is the delta T. And the good thing is you can quote the delta T in either absolute scale or Celsius scale. Same thing. The mass of the bar is given to be 525 grams. Determine the specific heat of the silver. Okay, so this one just a straightforward plug and play. Heat equal to mass times specific heat times the change in the temperature. What you want over here is the C. So you just take the heat divided by mass times delta T. The only thing that you have to be concerned with a little bit is just the units. Okay, so the heat, take a look at this one first. Okay, it's already in kilojoule. So you can put 1.24 kilo is 10 to the third joule. There you go. Kilo is 1,000. Divided by, now the mass is in gram. You can turn this into kilogram by divided by 1,000. So it's going to be 0.525 kilogram. Very good. All right. And times the delta T change is rises by 10 degrees Celsius. That is already 10. Done. Whatever that number is, that is your specific heat of silver. All right. This one is good. No big deal. So what kind of problem that can be applied, I mean, in a more, well, practical way? So take a look at this one. I think this is very, I think this is realistic because you guys, maybe some of you have already tried some solar energy, maybe. All right, so take a look at this one. A water heater is operated by solar power. Okay. Oh, there's a question here. Okay, that's a good question. So there's a question about, okay. So let me go back, and there is questions a little bit just to make sure that you guys okay with the units over here. So every time you have the delta T, okay, this one works in both Kelvin and Celsius scale. That's fine because the change of 1 degree Celsius is the same as the change of 1 degree Kelvin. But when you are dealing with the equation that has just only the temperature in the equation, that is when you need to use the Kelvin scale. Does that sound good? All right. So if the T is only the parameter in that equation, then stick with the K. Okay. All right. Oh, there's a question on the past slide why the water has a high. Okay. All right. Here we go. So one more time. So over here, all right. That's a good question, actually, just to make sure that you understand this one first before we move on. So during the daytime, the water and sand, yeah, get the same amount of energy from the sun. Okay. So at least let's say Q are the same. Okay. However, you can feel by walking, and then you feel from your feet that the sand is hotter than the water in the sea. So that means the delta T of the sand is kind of big because it's hotter, right? But the water is kind of small. Okay. All right. But knowing this, it means that the heat capacity of the sand must be kind of small, because the product between these two must be equal to the Q, right? Eventually. Okay. And the water must have the bigger C because it doesn't show up as the change in the temperature much. So the temperature rise maybe only like 1 or 2 degrees when the sand is maybe heat up 5 degrees, for example. And that is a showcase that the ability of the water to store energy must be higher. Okay, does that help? It's like I'm talking exactly the same as before. All right. Okay, does that help? Okay, so that means it's like if you take a kilogram of sand and a kilogram of water, okay, and have it sit under the sun during the at noon, let's say during the daytime, and then you see that okay, the sand is hotter. That means the specific heat or the heat capacity of the sand must be lower. Okay, all right, so that's what it is. Thank you. Okay, all right, so come back here. So we have a water heater operated by solar power, and you have a solar panel that is collecting the energy from the sun. Let's say if the solar collector has the area of 6 square meter, so somehow you have a solar panel. Oh, let's turn it off a bit. Okay, and then somehow you just collecting the energy from the sun. And then the area of this is 6 square meter. And it turns out the intensity, I don't know you guys remember this one or not, but if not, then we'll look at the unit. Not too bad. Here we go. The energy from the sun through the intensity value is 510 watt per square meter. So that means every 1 square meter of the area, you will receive power from the sun of 550 watts. Okay, cool. So that's the unit of intensity. It's the power per unit area. All right, but just by looking at the units is good. How long does it take to increase the temperature of a cubic meter water from 20 to 60 degrees Celsius? All right, so this is a good question. I don't know. I want to know how long do you have to wait if I want to use the energy from the sun to warm up the water from 20 to 60. So first thing first, how much energy do you need to warm up the water of a cubic meter from 20 to 60? All right, so we can calculate the amount of energy that you need to transfer to this water from MC delta T. Does that make sense? Okay, so far so good.
Okay.
What is the mass of a cubic meter water, guys? Cubic meter of water, what is the mass of this? Hmm. Just kidding. Oh, thank you. There's an answer here. 1 ton. Very good. So it's a ton of water. That's a 1 cubic meter water. Right? That's kind of heavy, right? It's one. So it's 1,000 kilogram. Very good. Thank you. All right. So now we know the mass. We know the specific heats of water. All right. We can go back and take a look at this one. All right. I can use this numbers right here. That is a joule per kilogram Celsius. I can approximate this one to be like, 4,200. That's, pretty good. All right. Approximately about there. Okay. So it's a joule per kilogram Celsius. All right. And then the temperature change, you're going from 20 to 60. So the change is positive 40 Celsius. All right. And the reason I want to put positive in here, just for you to get the familiarity with the sign. Eventually, we're going to have the sign associated with the Q. But for now, it's increasing, that you know that you have to supply the energy to the water. That's kind of clear. Okay, that's it. This is the amount of the energy that you need to warm up the water. Okay, but now you get this energy from the sun that gives you the 550 watts, and you collect it from a 6 square meter panel. So that's fine. So I can say the power from the sun is going to be 550 watts per square meter, and you just multiply by 6 square meter. Yeah, that's no big deal. So this is what you get. It's going to be 33,000 watts. Is my number is correct? I hope. Okay. All right. So that is a 3,300 watts of power that you got from the panel. But then if you still remember the concept or the definition of the power is just the energy per unit time. Is that right? Yeah, makes sense? Yep. It doesn't make any sense. It's just definition. Okay. So energy per unit time. So that means you can calculate the amount of time that you have to wait by taking the energy that you want divided by the power, which is right now is 3,300. All right. And that's it. What you are dealing with right now is just that Q is the amount of energy that you need right here. Okay. Just plug that in. And then you're done in second. Okay. Sounds good. All right.
Okay.
Not too bad. All right. So this is just a straightforward application of this expression, Q equals to MC delta T. Okay. Did I make any mistakes? Number calculations here? I hope everything is good. 550 times 6. Okay. All right, guys. This is good. All right. But that's not the fun of this part. The fun of this part is this. Sometimes when you give a substance some energy, you say, all right, we expect the temperature change, right? But sometimes it's not. The exception happens when you hit the phase transition. Right? During the phase transition means you want to change from one state to the other states of matter. For example, you might want to go from solid to liquid. All right. Or you can go backward from liquid down and you freeze things up to solid. Or you might want to go like vaporization. You want to go from liquid to gas, like when you boil water and you vaporize everything. During that vaporization, during the phase transition period, the energy that you supply to the substance doesn't get to the change in temperature anymore, but it's going to get used for the transition of the phase. Does that make sense? So the energy that you supply during that phase transition period will be used to change the phase of that substance. The amount of energy that you need to change that phase of the substance, we call it the latent heat, right? And the Latin, it just some Latin word saying it's hidden. The reason it's hidden because you cannot measure the temperature change anymore. It's just only the phase change that is occurring at that temperature. Okay. So this one is going to be a simple relationship. It depends on how much energy you supply and how much energy that it's used to change the phase per kilogram. We do it per kilogram all the time. All right. So that latent heat is considered per kilogram. This is per kilogram. So it depends on how many kilogram of the material that you're going to bring in to do the calculation. You multiply it by the mass, and then you know the amount of energy Q that you need to supply to that substance to make it change the phase. Okay, so it's a simple product, mass times the latent heat. Cool. All right.
Okay.
And then, of course, there are some names associated with the transition between, for example, solid to liquid. We call the heat of fusion. So it's a latent heat of fusion. If you want to go backward, you want to go from liquid back to solid, there's a heat of solidification. So the name is going to be sort of like long over here. You want to go from liquid to gas, that vaporization. And you want to go backward, when you go gas to liquid, that is the condensation. All right. But you guys know that actually each pair will have exact same value. So if you take this much to go from solid to liquid, it will use the same amount, but in the opposite direction to go from liquid back to solid. Does that make sense? Oh, I keep touching the back button. Sorry, guys. Okay, does that make sense? Okay, so if you have a solid you want to go to a liquid, okay, you have to supply energy to this Q equal to ml. But on the other way, if you want to go from liquid back to this, you have to actually extract the heat out from it, the same amount. Okay, guys, with me so far? Okay, so to go from solid to liquid, you have to give the energy to the object. Give to the object. I'm going to say this is plus. You add something to the object. On the other hand, if you have a liquid and then you extract or you pull out the energy from the liquid, that is the negative direction of the heat. You guys with me now? So heat is energy transfer. You're moving the energy around. But then, of course, there must be two directions. You can move it in or you can take it out. So now I'm going to start define the direction. If you have a positive heat, it means you're adding the heat to the system. If you have a negative heat, it means you extract or you draw out the energy from the system. Okay, one is positive, one is negative. Okay, all right, so keep going. All right, I hope that building something up. This table will give you a list of latent heats of fusion or vaporization of some common substances. All right, we can refer back to this table when we do calculations. Yeah, and I think maybe the one that we're going to use a lot is going to be water. So water takes this much to go from solid to liquid per kilogram. And the water will take this much of energy to go from liquid to vapor. You vaporize a kilogram of water, you have to use this much energy. All right, so that's what it means by the latent heat. Okay, cool. Any questions so far? Still with me? All right, guys. Very good. All right, so with that, so this gives you like a grand things that gonna happen every time that you supply some energy to a water. Let's think of this one like, let's say if you have like 1 kilogram of water, you can start from like a super like deep, like ultra frozen ice, right? So you can have an ice at negative 30. And then now you start supplying the energy. So this is the horizontal axis over here is the energy added to that water. So of course, first period of this one, the ice will start to increase in temperature. Okay, with me over here. All right, so until it hits the phase transition temperature, and everyone knows it at 0 degree. During that time, you won't see any temperature change, but ice will start to melt. Okay, so the more energy you supply to it, the more liquid water will start to come out from your system, right? Ice melts, get more liquid water, keep melting until all the ice has already melted. You get 100% liquid phase water. After that, if you still keep adding the energy, then it will start to rise in temperature again. Okay, so the water will go up again. So this is the two scenario over here. During this phase transition, there you go. You can calculate the amount of heat required during that melting process using just an M times the latent heat. And once you doing just a simple heating up of the stuff during this phase, you use MC delta T. Does that make sense? All right. So now the water will get higher and higher in temperature. It's getting hotter and getting hotter until it hits 100 degrees Celsius. That is the time that you hit the phase transition again. So you start vaporizing things. So during that phase, you won't see any temperature change. Okay. But what you get is you're going to get, oops, sorry, it's supposed to be highlighter. You're going to get, here we go, another change of the phase again without changing any temperature. So during this phase transition period, more of the vapor will get generated, right? So you have less liquid, the liquids turn into vapor, you just keep vaporizing water until all of the liquid water has been vaporized. That is the time that those vapor will get higher in temperature. So if you still keep supplying the energy to it, that vapor will be super, super duper hot. right there. All right. And then you get like a super hot steam coming out of this. And this is a reason why every time that you get the steam of water from maybe the rice cooker or whatever, the boiling pot, it's really burning, right? Because it comes with a lot of energy in it. Okay. So the steam of water is super duper hot, right? Because of this.
Okay.
Right? It's not because of this, but now we know why, right? It's huge. It's huge amount of energy that it's tag along with those vapors. Okay. Sounds good. All right then. Oh, I think I know why. Okay. All right, guys. So far, so good. Next. Now, so the cool thing about understanding this kind of thing is now you know the direction. There's one give, one take, right? There is put the energy to the system, take the energy out of the system. So the fun things, all this one is called calorimetry. All right. This is a stuff that they study water during the first uh oh, I have some going on with my computer. Okay, sorry. Okay, so over here, then what we can utilize this equation to understand the dynamics of stuff is by doing this calorimetry experiment. So what we're using is this. We incorporate everything that we have learned up to this point. Okay, for example, over here, if I have one object having the temperature, no, let me call it object one, and then I put this in thermal contact. Now I can use this word now. Oh, it doesn't seem to contact well. Sorry. Yeah, okay, there you go. Touch. Yeah, this is another temperature T2. Okay.
Okay.
And now everyone knows from the perspective of the thermal stuff that we have been studying, that will be energy transfer due to the temperature difference. So if T1 and T2 are at the same temperature, they are in thermal equilibrium, there will be no energy transfer. But let's say if one is hotter than the other. So for example, I might just say, okay, let me call this one is the hot one. So this is T hot. And the other portion of this one is colder. So now I'm gonna just call this one T cold. And now you know that there will be the energy flow from hot to cold. With me, guys? That is the heat. This is heat. Energy transfer. Okay. However, because in this scenario, you only have two sides of the system, the hot side and the cold side. So you will say that, Ajahn, the amount of heat that enter the cold part must be the same as the heat that flowing out from the hot part. Does that make sense to you guys? Okay. So that means if I call the left side to be Q hot and I call the right side to be Q cold, what I'm saying over here is the amount of energy that leaving the hot part must be equal to the amount of energy that enter the cold part. Cool?
Okay.
But then because we already had the direction, so what I'm having to say, if I don't want the absolute sign in my equation, I have to say this: Q hot must be equal to negative Q cold. Got that one now?
Okay.
Done. So it sounds tedious to you guys, but I would like to emphasize on the sign now because we have to set up the firm background for the next week. So you can pick and choose either one of these two equations. That's your choice because now you know the final answer will be exactly the same. Okay. However, the bottom one, this is the one that you take into account the direction of the heat flow in and out. In means positive, out means negative. But on the top one, well, you just take the magnitude and I will show you what's the difference between the two, all right, to finalize today's lecture. Sounds good? All right. So we know that that has to be because your system has only two sides. I can actually draw like a boundary for the whole thing, right? If I draw this whole thing, hey guys, take a look at this. This is my everything. This is my everything. So in the thermodynamics sort of theory and everything, we call this like it's already like the universe. That sounds really weird. But right now, our attention is only within these two, and there's nothing else beyond these two. So this is it. Is isolated, isolated. Okay, and we'll talk more about this sort of universe, environments, isolated system, on and on. But you can consider that this as an isolated system. There are no interactions with everything else. They are only interact with each other. So that's why we can say with confidence that by the conservation of energy, the energy that flow out from the hot side must enter the cold side because there are nowhere else to go. Okay, all right. So let's take a look at that. Here we go, guys. So this is going to be the problems that finalize today's lecture. Sounds good? All right, having fun? All right, maybe just two, last two. All right, but from the understanding, you should be able to do this like naturally. Naturally, I don't know. You have 500 grams of ice and it's added to an insulated cup that contains 200 grams of water at 50 degrees Celsius. What is the final temperature? Is that easy question? I think that's easy enough. All right, so let's have a water. Here we go. All right, let's put in some water here. Okay, we're good. That's my water. All right. And now I'm going to have ice adding to this. So we have ice cube thrown into this. So in terms of the diagram, what you have over here is one side of this thing is ice. One side of this thing is water. Does that make sense? Yes? Okay. So you put ice into thermal contact with water. And this is a whole isolated system of yours. There's nothing else. There's no air. There's no, you don't even care about the cup itself. You don't care about the container. That's nowhere else. You are only care about the interactions or the transfer that it's going to happen between ice and water. So that's why in your diagram, you only have these two. And that is your boundary of everything. That's what it is. Okay. All right. Now, come back to our business over here. Now the ice is the cold part. The water is the hot part. Because you don't know what is going to end. So let's assume that the final temperature equal to X then, let's say. Okay. So you're starting with the water at 50 degrees Celsius. And you have 200 grams of ice. I'm sorry, of water. But for the ice, you have 500 grams. And you know, because it's not like a super frozen ice or anything, it's supposed to be sitting at 0 degrees Celsius right there. All right, here we go. So there are two parts or two sides of this system. So definitely the energy will flow from water down to ice. You guys with me? All right, so you have Q hot and you have Q cold right there. Let me put the absolute sign there for now. That means there is an amount of energy flow from hot to cold. Okay, how much? All right, let's start from the water because at first the water is at 50 degrees Celsius, but then eventually it's going to reach X degrees Celsius. Okay, so the energy will have to leave the water. So let me use the equation Q, which is Q hot right now, is MC delta T. Okay, you guys pay attention to this. I don't have any absolute sign here. Mass of the water is 200 grams. So let me put it in kilogram, 0.2 kilogram. Pretty good. C of the water, let me put just C of water for now. We can always substitute this one using the table in the front. No big deal. What would you like to put in the delta T, guys? Just kidding. What would you like to put in the delta T? What would you like to put here? All right. The delta T is temperature change, right? All right, very good. There are some some answer pop up here. 50 minus X, T minus 50. All right. 50. All right. So the answer is delta is the change. Change, here we go. This is the one that I want you to pay attention here. Delta means final minus initial all the time. All the time. All right. If I have my money in the morning, 10 baht, for example. And at the end, I have 9 baht. What is my change of the money in my pocket? I have to put 9 minus 10 is negative 1. So negative will show that my change is in the negative directions, which means decreasing. Okay. Delta always means final minus initial. So over here, what is your final temperature? Well, then that's X. What is your initial temperature? It's 50. There you go. That's what you have to put in here. You guys with me now?
Okay.
And the good thing about this one is this equation doesn't have any absolute sign whatsoever. The mathematics will take care of the final answer itself because everyone knows X eventually must be less than 50. So at the end, the Q that you're going to get out of this is going to be a negative number. And that is perfect because we said negative heat means heat is leaving. Negative heat means heat is being taken out. Isn't it cool?
Okay.
See, so if you stick with the equation and then you stick with the definition of everything, the equation will take care of the sign by itself. All right. Okay, got that? Now, let's do this on the cold side. Q cold. So what happened to the Q cold? The ice. All right, so what you're aiming for is, of course, the ice starting from 0 degrees Celsius as a solid phase. Eventually, you're going to reach X. So first thing first, it has to melt, right? Before it can reach the water at X degrees Celsius, it has to melt. So first step, you have to take the M and you melt them all first. It needs M times L amount of energy to melt this ice. All right, once all ice has been melted, then it starts to rise in temperature from 0 degrees Celsius all the way to X. So I'm gonna have to add MC delta T for that. Okay, does that make sense to you now? Okay, so for here, let me put subscript ice here, mass of the ice here, but C over here I can say is water. Okay, let me space this one out a little bit so I have some more room to write C of the water, delta T. Okay, makes sense? All right, so let's try this. Mass of the ice is 500 grams. So let me put 0.5 kilogram here. L of the melting process, you can look it up on the table. That is fine. Let me put it there. Plus, now you already melt everything. You will have to raise the temperature of the liquid water at 0 degree all the way to X. So I'm going to say it's still the mass of the ice, same amount of water, liquid that you're going to get. Now you times only C of the water now because it's already in a liquid phase. What should put here? Well, of course, again, because you start from 0, you end at X. So it's going to be X minus 0. With me, guys? And that's it. From here, you already have two values of the heat that you want to transfer between each other. All you need to do is just equate them, right? Because you know they must be exactly the same. But it's your choice. You can equate them through the absolute sign. If you want to take the absolute, that's when you have to make sure that you have to do this. It's going to be 50 minus X instead. Am I confusing you in any way right now? Because if you are taking just only the magnitude, which is the value, right? You know that X is always less than 50. So to be able to get just a positive numbers out of this, you know in your head that you have to do 50 minus X for you to get a positive number. All right, so that's what it means by applying the upper expression right here. And this might go more naturally with you guys because you might feel, Ajahn, I know in my head where should be the final temperature, what is the initial temperature, so I can calculate the magnitude of the heat. That is fine. So this one works. Or on the other way around, you can just use the second expression, just say Q hot equal to minus Q cold. Right? Or equally, it's minus Q hot equal to Q cold, doesn't matter. All right. But as you can see, no matter what you do, at the end, you have to flip the sign and you end up with 50 minus X anyway. Does that
Okay.
come in full circle here? I hope. All right. But benefit of doing this second line expression over here is like you stick with the definition of the delta, you stick with the agreements of the direction of the energy flow. Heat flowing in mean positive, heat flowing out mean negative, and then you use the actual directional heat and equate them properly. So that's why you need an extra negative sign in the front. But because this one is natural enough for you to, all right, Ajahn, I don't care about the directions. I don't want to deal with the delta. I don't want to know the heat in, heat out. Just too much. That's fine. You can just, calculate the magnitude of the heat involved in each side of the process and then just equate them. You would get the same answer anyway. Okay, sounds good? All right, but at the end, just equate these two and then you should be able to evaluate the final temperature X and you're done.
Okay.
All right. Sounds nice. All right, so I hope this one showcase how to utilize this Q equal to MC delta T and Q equal to ML in the actual problems. And the problem that you are dealing with this kind of thing, like you have one mixed with the other and all that stuff, that is the calorimetry. Okay, so it's the one that you try to equate the heat flow between portion in your system on and on. All right, sounds like fun over here. All right, we'll deal with this kind of thing more and more in terms of the sign, right? It might not confuse you at this point. And actually, it might even more confusing to try to apply this kind of expression now because things might just too straightforward already. It's just like, Ajahn, it's too much. Why you have to care about the direction now? Okay, but it will be much more useful or much more crucial to our calculation later in thermodynamics. All right, maybe not now. Okay, sounds like a good plan here. All right, guys. So if this is good, I think this is a good place to stop today's lecture. All right, we have one more. If you're up for it, feel free to try this one during the week before we see each other again on Monday. But if not, I'm going to use this example as the review questions first time we see each other next week. Sounds like a good plan? Okay, all right. Any questions? Okay, I hope not. Ajahn Kap. Oh, upload. Yes. Oh, written slides. Okay, that's a good thing. Okay, so I'll do that. I'll do that. So, all right, what I'm going to do is, all right, there will be a YouTube video for you to review just in case, and I will convert this into a PDF and post it in the Google Classroom. Sounds like a good plan, yeah? All right. Okay, not a problem. Okay, that's a quick question. Oh, you're welcome. Okay, so okay, I think this is a good question. All right, so there is a question about using the latent heat. Yes, every time that you have the phase change, you always need ml in your equation. Yes, yes, all the time, definitely. For example, like what you are asking, if you mix the vapor, the steam of water with the ice, so the ice has to melt and turn into water. Okay, for the steam, you have to ml first to condense the steam into liquid water, and then you use mc delta t for the temperature change. Yes, that's what it is. Very good.
Okay.
Yep, always. All right, guys, that's very good question. All right, so that's it. All right, so guys, see you on Monday. All right.